We have an ellipse here where this is one focus. I'm going to switch on another focus. There are two foci here. At one foci we'll consider sun, and at another foci it is empty foci. There can be nothing. Now we have this orbit of the planets. This orbit is of Mercury. Look at the distance from Mercury to Sun. It is 1 atmospheric unit, whereas its eccentricity is 0.4. What is this eccentricity? Let us look at the value of eccentricity here. When I decrease the value of this eccentricity, I am going to bring it near to 0. Look at the distance between the foci. The foci will join together. If I increase the eccentricity, the foci will be away. This orbit looks more like of an ellipse. This is more elliptical when compared to this one. Therefore we can say that a circle is nothing but an ellipse where two foci are joined together. When we consider the case of Venus, we can clearly understand that Sun and the empty focus are together. That is, the orbit of Mercury is very circular compared to Mercury. If we take the case of Earth, let's go to Earth. Look at this. The distance between Sun and the Earth is 1 astronomical unit and eccentricity is 0.017. That is, the Sun is almost at the center of the circular path. That's why we don't feel any difference between whether the Sun is away from the Earth or near the Earth. Not in the case of Mercury. In Mercury, look at this distance. This distance is very small compared to this distance. The first law says that sometimes the planet may be near to Sun, sometimes it is away from the Sun. This can be evident. This can be case of Earth. Look at, and so first law says that sometimes the Sun, sometimes the planet will be. Let's go to the second law.
Let's go to second law. I have taken Mercury here. Okay, and I'll start the animation. This law, when this planet is moving in circular path, when it comes near to the planet, when it comes near to the Sun, the planet moves faster. When it moves away from the Sun, the planet moves slower. Let us increase the eccentricity and start the animation. To understand, we'll start sweeping here.
now look at this. This is equal to this. A fractional sweep size is always the same. A fractional sweep size is 7.7%. The is longer than the height. Here the height is smaller, is greater than this base. Therefore we can say that by looking, we can say that these triangles are equal in area. An imaginary line drawn from planet to the sun sweeps equal areas in equal interval of time. This is what the second law says. The meaning of the second law is when the planet is nearer to the Sun, it moves faster. When it is further away, it moves slower.
We'll take the case of Earth. Is it true for Earth also? Does Earth move faster sometimes and move slower sometimes? Let us check what may happen. I'll start the animation. I'll increase the rate of animation and start sweeping.
Now look at the size of the triangles here. All triangles are almost of equal area. That means that the planet is not moving faster or slower at any point. This is because the Earth's orbit is almost circular. And we'll go to the third law. And third law says when the planet is away from the Sun, let's go to third law. When the planet is away from the Sun, the distance will be further. When the when the distance is further. This is taken as semi-major axis. Look at this. The third law says there is a relation between the period and the semi-major axis. Semi-major axis is nothing but the eccentricity. As the eccentricity is more, the length of the semi-major axis is more than this length of the semi-minor axis. Here, as the distance increases, period also increases. Let us see how is that true. In order to prove that, observe this value. For Mercury, this time A is 0.387. Look at this, 0.387. The distance between Mercury and the Sun is 0.387, whereas the time period is 0.241. If I increase the distance of the semi-major axis, for example, if I take it as 2, I'll take this as 1. What is 1? Huh? 1 is Earth. I'll take the case of Earth. Earth is 1 astronomical unit. 1 astronomical unit is equal to A cube. This semi-major axis is taken as A. A is nothing but Earth's distance between the Sun and the Moon. It is taken in the case of AU. If I go to Saturn and start animation, look at the time period. The period is 29.5 years, whereas the distance between the Sun and the planet, average distance between the Sun and the planet is 9.54 astronomical units. Therefore, the square on the period is equal to cube of the average distance between the Sun and the planet. This is the Kepler's third law of planetary motion. It says that as the planet moves away, as the planet is away from the Sun, it takes more time to revolve around the Sun.